All right, well, let's get started. Just a couple of things first. I wanted to make sure everybody saw the announcement I posted on Canvas. All of the lecture recordings are going to be posted to a YouTube channel instead. The link to that YouTube channel is in the course syllabus. It's at the top. So if you have any questions about that, any problems with that, let me know. Just a reminder, we have our exam at the end of the week. It's going to be in person here, and it'll take the full class time, so we're not going to have lecture before or after. So once you finish your exam, you're free to go. It's 50 questions, it's multiple choice, and it covers everything from earth materials, geologic time, plate tectonics, and the stuff we cover on earthquakes. We're going to do tsunamis probably tomorrow and Thursday, but that's not going to be on the exam, just from earthquakes and everything before. If you have any questions or trouble with the material, I have office hours today from 4 to 5, and I'm also available most of the day. So if you need any help, let me know. My office is Penny 204. And my office hours for tomorrow, I'm going to move to Thursday, just in case anyone has any last minute questions as they're studying for the exam. So 4 to 5 on Thursday, and that'll be through Zoom or in person, whichever you prefer. And I think that's all I have for that. All right, well, let's get started. So last time we were talking about earthquakes and how they're felt around the country and how they're felt differently around the country due to local conditions. So for example, with the mineral earthquake in Virginia compared to another earthquake of similar magnitude in San Francisco, the one in Virginia was felt more, and that's mostly due to the local conditions, like poorly consolidated sediments. So that affects the amplitude of the waves from a seismic event. As you can see on that line along the bottom of the model, that amplitude is increasing and increasing as you travel outward from bedrock, which is more rigid, to consolidated, to poorly consolidated, saturated. So saturated sediment is really the worst thing that you can possibly build on. That's what's going to give you your greater shaking, and that's what's going to really affect any structures that are on top of it. So this is an example of liquefaction. So this is just regular old play sand that you can put in your sandbox at home. Once it's wet and you add water to it, they're going to end up tamping this down and putting some type of weight on it. So as he's just shaking it, that weight is going to sink into the sand. So if you think of just a coastal system, they have stuff buried like pipes represented by that ball to the right. So as you're shaking, you're bringing subterranean buried things up, and weight on top of it, you're kind of settling it out and bringing it down. So this is what's known as liquefaction, which is where these solids that are saturated end up behaving more like a liquid whenever you introduce shaking to it. So this is a big problem in the coastal United States, even though it's a good thing that we don't have too many earthquakes, because this would happen quite frequently just because we have so much sediment built up on the East Coast, mainly because it's older. A lot of those rocks from the Appalachian Mountains have weathered. The sediment's been carried down to the coastlines, and the coastlines are made up of that sediment. So luckily, we don't have too many earthquakes on this coast. We can also have side effects due to volcanic activity. Volcanic activity and magma creates instability in solid rocks, enabling them to build up more strain and break and fracture. So whenever you have an eruption, you're going to get an increase in earthquake activity. You get a lot of earthquakes leading up to the eruption, right before it, during the eruption, and a little bit after the eruption, as magma is pouring out onto the land, destabilizing the rocks that are pre-existing there. So earthquakes are really helpful in detecting volcanic eruptions, which we use frequently. We can also detect earthquakes from meteorite impacts. Doesn't happen very often, but meteorites create enough air pressure and impact to create some type of seismic wave. So we can tell, even if we don't have video evidence or evidence from satellite data that a meteorite impacted, we can see it in seismographs. There's typically no lead up to the earthquake event whatsoever. It's just really quiet and then boom, big seismic event, and then a little bit of aftershocks afterwards. So even meteorite impacts cause seismic events that we can pick up with seismographs. We can also think more of the human impact of how we can create seismic events. So nuclear testing, for example, we've had a lot of that in the past, and certain countries are doing it continuously. Usually those tests are conducted underground to prevent any radiation from entering the atmosphere. So much like with a meteorite, there's no precursor earthquakes. There's nothing leading up to it. All of a sudden you have a very high localized event with a huge magnitude. That's how we can also detect nuclear blast. Also fracking, we talked about Oklahoma and how they have the most frequent number of earthquakes in the country, even more than over in Cali. And that's because we're practically destabilizing rock that has never been destabilized before. We're creating more stresses, we're adding more stresses, increasing the strain that those rocks are experiencing. And then we're removing some mass, in this case, natural gas, from the ground, and it has all this pressure built up, and now it has a void space to move into. So you're going to get more cracking, you're going to get more movement and motion. So that's going to continue to happen as we continue to frack. So this is a map of, this is a huge database that has collected data on human-induced earthquakes. So let's actually, let's see if it'll work here. Where is it? There it is. Okay, so this is that exact site. We're just going to take a look at what we can find. So let's take a look at Iceland up here. So they have a lot of human-induced earthquakes. They're right along that rift zone, that mid-Atlantic ridge. What do you think would be the main cause of human-induced earthquakes in Iceland? What's something that they do a lot for their energy? Does anybody know? It's not hydropower, but it's a different renewable energy source. I thought I heard it. Not solar. Think of heat. Geothermal, very good. Yeah, so because Iceland is situated right on the rift zone, they get all that hot magma coming up. They have a lot of heat that they can tap into for their energy. Iceland is completely carbon neutral as a country. They do a combination of geothermal, they do some offshore wind, and their offshore wind has some tidal energy generators as well. So as the tides come in and out, that runs a turbine that'll give them extra power. So geothermal energy is the method of drilling into and heating water pipes through just the heat from the earth, the natural heat that's coming up. So that ends up destabilizing a lot of the areas around it. So they don't get frequent earthquakes, but they get some. And they're usually around like a magnitude 1, magnitude 2. If you were standing right over top of those, you probably couldn't even feel them. There's nothing really to write home about, you know. Let's take a look over at the Americas. Let's zoom in here. All right, so what do we have going on over in Ohio and Pennsylvania? What do you think this is? What's this big unit of fossil fuels over here? Does anyone know? Probably heard of it, but you probably can't think of it at the moment. This is the Marcellus shale gas. So this is all that natural gas that we do for fracking in the East Coast. Pennsylvania is covered in pipelines. All those pipelines converge in Philadelphia. Then all that natural gas is shipped all the way up the I-95 corridor from Wilmington, North Carolina, all the way up to Portland, Maine. So there's a lot of natural gas here. So we get a lot of earthquakes in this area as well. Obviously, we have over here in Oklahoma, all of those from natural gas. What are these green ones in Nevada? We can think of what those would be. These aren't recent. This is just total human-induced earthquakes. So what do we think was going on in Nevada that would create an earthquake? Nuclear testing. That's the Manhattan Project right there, 1940s. So those were picked up from seismographs all over the world, and nobody knew what it was except obviously the people working on the Manhattan Project. We also have a couple of weird ones. This one is called CCS. CCS stands for carbon, something carbon sequestration. So this is where one of these instances where what we're trying to do is take atmospheric carbon out of the atmosphere. Knowing what we know about the carbon cycle, the best thing to do with carbon and atmospheric carbon is get it to the point where it's in a sink, which is what a fancy term for basically it's buried somewhere and doesn't enter the atmosphere again for millions and millions of years. So we're trying to accelerate that process. Some government agencies and environmental groups are trying to accelerate that by extracting carbon out of the atmosphere, turning into basically bricks and just burying those bricks deep underground so it doesn't enter the atmosphere again. Now, that's just a drop in the bucket with what we're doing with emissions, but it's a feasible option that we can look for in the future. So that's also causing a lot of earthquakes. All right, let's get back to the rest of the lecture. All right, so now we've discussed the location portion of the earthquake hazard. Now let's talk about the magnitude. What's the shaking intensity and the energy released from each earthquake and how that impacts us. So we've got three different ways of measuring earthquake shaking. We have the modified Mercalli scale, which is also known as modified Mercalli intensity. We have the Richter scale. We have the moment magnitude scale. So we're going to go through each of these and talk about how these are useful for scientific studies as well as policy making. So the modified Mercalli intensity is more of a qualitative measurement. There's not a lot of numbers in it except for economic damage and casualties. So this is more of the human element. So it's based on a scale from 1 to 12, and it's based on observed damage to structures. So if you look at a freeway and it's collapsed or it's cracked, buildings, if they're also collapsed or if they're damages to the foundations. And these can vary widely based on location. They can vary even within single family. Some people feel it a lot, feel the shaking intensely. Some people don't feel the shaking at all. So this is, it's not a very scientific measurement, but it's useful to see how widespread an earthquake has affected the human population. So this is what it looks like. And you have the scale on the left, and just to brief description of what that looks like on the ground on the right. So if we look at number 7 here, we have damage negligible in buildings of good design and construction. So if something is designed well and up to code, you're not going to see anything on it. In ordinary structures like housing, suburban housing, your typical ordinary residences, you'll see a little bit of damage. Considerable in poorly built or badly designed structures. These are like those real shallowly built shanty towns. That's where we'll see a lot of that big damage. But in a lot of different earthquakes, we'll see poorly built things like that destroyed entirely. See damage to chimneys, and vehicle drivers will feel it. A lot of people that are driving at the time of an earthquake won't feel it because they'll feel the vibration from the engine, from their car hitting bumps. So it's really hard for them to perceive it. But if it's large enough, they'll definitely tell that something's not right.
Excuse me, Professor, we can't.
So just going from a 7 to now a 9, we have considerable damage in structures that are up to code, those earthquake-proof structures. We have complete damage and devastation of poor neighborhoods. We have breaking of underground pipes carrying water, sewage, natural gas, so that could be an even bigger problem. So just from a 7 to a 9, we're going from not a lot of damage to significant damage. So like I said, the modified Mercalli intensity is based on what you, the population, feel and what you, the population, report. So the USGS, as we talked about, has this Did You Feel It program where they'll just, you can log in and say, oh, I felt this. This is what it felt like. This has this questionnaire to be, it's targeted to somebody who doesn't understand how earthquakes work. So they'll be like, how long did the shaking feel like it lasted? Or where were you when it happened? Or very simple questions that they can get a lot of qualitative data out of. And this is how we create shake maps. So shake maps are basically how we can see how widespread the shaking was. And that will also end up being useful information for establishing how bad an earthquake is and how wide-reaching it is. It can also help local governments and policymakers to enact some repair and reconstruction missions. So that'll be very useful for them to have. Now we're in the Richter scale. This is a quantitative measure. So Charles Richter, who is a California seismologist, really smart guy. So he was measuring specifically the max amplitude of S waves or secondary waves, the second ones to arrive. So any seismic station that has a seismograph can calculate this. And this is on a logarithmic scale. So it's all based on the local magnitude, what happens at the site of the seismograph, not necessarily from the source of the earthquake, but from that specific site. So each seismograph is going to have a different magnitude for the local magnitude, and then that's averaged into calculating the actual magnitude. So this is just some review. What do you guys think is the S wave? Is it A? Who thinks it's A? Who thinks it's B? Who thinks it's C? All right, so the answer is B. So that initial one at A, that's our primary wave. That's the first one that arrives. It's the fastest, but it's also very small. It's not damaging. It's one of the body waves. The secondary wave is B, which is a lot bigger. It's felt a lot more because it has this perpendicular motion to the wave. It's up and down. So seismograms can feel it a lot more than P waves. C, those are our surface waves. Since the seismic station is on the surface, it's going to catch those the most, and you'll see the most amplitude from those waves. But these aren't secondary waves. They're the two slowest waves, but they're the most damaging on the surface. So C, those massive ones That's our surface waves. So earthquake magnitudes on the Richter scale are, it's a logarithmic scale. So each number is 10 times greater than the one before it. So strong earthquakes from magnitude 6 and up to a magnitude 7, they happen, depending on where you are, they happen pretty significantly and frequently. California gets a lot of magnitude 6s, and sometimes a little less, maybe 5.8, 5.9. Your greats, your magnitude 8 and higher, they're very, very uncommon, incredibly uncommon, because they're so vastly damaging, and it takes so much buildup of strain on the rocks to create that much force to create a magnitude 8. It doesn't happen very often. A lot of times there's smaller releases of stress in rocks, so you'll get a lot of smaller earthquakes. It takes a long time to build up enough stress to create that huge earthquake. But if you look on the right side of this table, you'll see the average recurrence interval of these. So your great ones, you probably have it maybe once a year, very rarely, but maybe once a year. And these are statistics, so it's not like it's guaranteed to have one every year. There's just a chance of having one each year. And then as you get to smaller and smaller earthquakes, you're increasing the number in frequency, which makes sense, right? You're gonna have a lot more smaller earthquakes, like Oklahoma, the most frequent earthquakes on Earth, but they're all magnitude 1, magnitude 2. Magnitude 1 isn't even on here because sometimes we can't even detect them unless we have seismograms that are localized around that area. So like I said, this scale is logarithmic. It's a power of 10. So basically a magnitude 5 means the amplitude is 10 to the 5th. It's raised to the power. A magnitude 6 is 10 to the 6th, raised to the power of 6. So if you divide those two, that means you have 10 times more ground displacement, 10 times more amplitude than the previous number. So the difference between a magnitude 5 and a magnitude 6 is huge. It may not look like much on paper, but it is a significant jump in energy and in amplitude. So if you look at this graph, we have our magnitude increasing on the x-axis. This is the actual measurement on the y-axis. So you've probably seen logarithmic plots before where you have the lines close together, and then as you go out, they get further and further apart. We have the same thing here. Look at how close from 10 to the 1st to 10 to the 6th are, and then you get all the way up to 10 to the 9th. So this is how vastly different these are. A couple of examples of really devastating earthquakes on the right, or large earthquakes in this case, not necessarily always devastating. Loma Prieta at around magnitude 7. That was a pretty big earthquake. It wasn't hugely devastating, but it was still pretty large. Then we get to San Francisco, which was a huge earthquake and also very, very devastating. Caused a lot of fires, pretty much destroyed the city of San Francisco. New Madrid in Missouri in 1812. This is a pretty fun one. This one caused so much uplift that the Mississippi River ran backwards, which is crazy because the Mississippi River is enormous and captures so much water. For it to run backwards, you have to have a lot of uplift and displacement. Then Alaska in 1964. This was one of the biggest ones recorded. Not as big as Valdivia, which is up there at the top at 8.9 in 1960. But Alaska was a pretty big one. It didn't have a lot of devastation because in 1964 in Alaska, not a lot of people lived there. So still not a lot of people live in that area. but we had a huge earthquake there. And then if you'll notice, Valdivia at the top, Alaska, there are a bunch more examples that are on this, but all these large earthquakes, everything that's above an 8 is coming from subduction zones. Those areas where the plates are being pulled underneath the overriding plate, that's where we get the largest earthquakes on Earth. That's where we get the most powerful earthquakes. All right, so let's do a quick math exercise. So we have our Mineral Virginia earthquake. This had a magnitude of 10 to the 5.8. So it was a 5.8 magnitude. Dove Creek, another one of a little smaller size in Colorado, 10 to the 4.5, a magnitude 4.5. So we're going to calculate the difference between those. So how much bigger is it? So if we divide 10 to the 5.8 by 10 to the 4.5, we get 10 to the 1.3, which if you put that into your calculator, that's 20 times more ground displacement. So magnitude is measuring amplitude as well as ground displacement, which means it's 20 times greater. Just in that 0.7 difference, it's 20 times greater and more powerful than the Dove Creek one. So let's try another one. So we have Tohoku earthquake in Japan over here on the right, 2011, magnitude 9.0. And we have the Mineral Virginia one again at magnitude 5.8. So go ahead and get your calculators out, try that out. Remember, it's the large one divided by the smaller one. So let me know what you get.
Excuse me, Professor.
What do you got? 1,585? That's right. Yeah, so it's just as simple as taking the greater one, raising it 10 to that magnitude and dividing it by the smaller one. And that's how many times more powerful it is. Does everyone understand the process? Everyone clear on that? Good. All right, and this is our third method of measurement. This is moment magnitude scale. This is the most scientific one we have because it's the absolute size of the earthquake. So we've got a bunch of different parameters. It's the measurement of the actual energy that gets released by that. So you have the rigidity of the earth multiplied by the slip along the fault, which is the displacement. And then we have the area of the fault, which is length times width. So the way we calculate energy, and energy is proportional to 1.5 magnitude, which just means that 10 to the 1.5 is 32. So all energy released is proportional to that number 32. So similar to what we were doing with our magnitude, let's calculate the actual energy released rather than just how much displacement is. So we have Dove Creek at a 4.5 magnitude, Mineral at a 5.8, same as the first question. We're going to raise that to the 32, which means we get 90.5 times more energy released. Same as before, you just calculate those exponents, you divide the larger by the smaller. So let's try that one. How much more energy was released in Tohoku versus Mineral Virginia? Go ahead and test out that equation and let me know what you get. Anybody have it? What do you got? 65,536. That sounds right. Whoops. That's right. Well done. So it's as simple as that. Just take the, you have a question? Yeah. Walk through how to get that? Yeah. Okay. So you have Tohoku. The Tohoku earthquake is a magnitude 9. Since we're calculating energy, not displacement, we're going to use 32 raised to the power of the magnitude. So 32, whenever we're using 32, that's what we're talking about energy released. So 32 to the power of 9, and then we're going to divide that by 32 raised to the power of the magnitude of the mineral earthquake, 5.8. So if we divide that, that's how we get 65,000. That makes sense to everyone? Whenever we're using 32, we're talking about energy. Whenever we're just raising it to the power of 10, we're talking about the magnitude, the amplitude, the displacement. All right, so we were able to kind of tell this before, but this is what it looks like from the frequency versus magnitude perspective. So that top row at the top, it's kind of hard to see. I'm going to have to fix these slides so that they're able to be seen on a bigger screen. We have for 8.0 and up in magnitude, we only have 1, 1, 0, 1, sometimes 2, and that's from 2000 till 2018. So not a lot, not a very high recurrence interval. And as we continue to decrease in magnitude, we're going to get more and more. So lower magnitude earthquakes are a lot more frequent, higher magnitude are infrequent, and that's lucky for us. So whenever we're talking about hazards, we really want to talk about mitigation and adaptation to all of these hazards, because that's what pays the bills. Governments and agencies pay geologists to figure out how to predict, to forecast, to prevent these from happening, and decrease the death toll and casualties and economic damage that happens from these. So obviously we can't stop an earthquake from happening. That's a great amount of energy that we can't even possibly think to prevent. Also, if you tried to prevent every earthquake on Earth, I'm pretty sure that would be pretty bad. You wouldn't have any displacement of the crust, tectonics would stop, and then Earth would become dead. So you wouldn't want to stop earthquakes. You want to have some release of strain and stress. But what we can do is we can predict, we can create more resistant buildings through different building methods and infrastructure methods, and we can educate. So one thing scientists want to distinguish is the difference between prediction and forecasting. So, for example, a prediction would be a magnitude 6.7 earthquake will happen in Parkfield, California on January 12th, 2017. That's really dumb. That's really dumb to think that at some point in the future, we can predict to the day that an earthquake is going to happen. That's ridiculous. That's somebody looking into their crystal ball and just pulling something out of thin air. Forecasting is what we do in science. Forecasting is what we do in meteorology, when it comes to seismology, as well as studying volcanic eruptions. We can forecast and we can say there's a 67% chance of a magnitude 6.7 earthquake happening within this time range. So while your typical layman would probably not be satisfied with this, you can at least take this information and say, okay, within the next 30 years, we can implement this plan to build more earthquake-proof infrastructure, to build better buildings, to have better evacuation plans. So that's something that you can at least, number one, it's scientifically accurate. Number two, you can still use that information and make good choices, good public policy choices with it. So in order to forecast, we need data. Scientists work with data, and data is just the lifeblood of creating good scientific observations. So for the short term, we want to know about precursors. Whenever it comes to earthquakes, there's always the foreshocks, the little earthquakes that build up right before a big earthquake. And then we have aftershocks afterwards. So if we study those short-term uplifts, those areas of subsidence, we can measure strain, and we can measure different emissions of gas in the area. Those are our short-term measurements. For long-term, that's where we're getting into more of the math, more statistics, to see what kind of probability we have of different earthquakes. Also, we have seismic gaps, which are areas of little to no seismic activity, which may change into more active seismic areas. So this is Parkfield, California. This is an area where they're doing a lot of both those short-term studies and long-term studies. They have tons and tons of instrumentation here in this area. So they have creep meters and tilt meters. Creep meters measure very, very slow movement of land, which is known as creep. Tilt is obviously measuring the angle at which the surface of the land is changing. It's also measuring pressure, which you can do through drilling, and it's measuring tension. Basically, you're installing these two rods in these two areas, and it's measuring the stress as those areas are getting pulled apart. So not only is it good for data collection, it's also really good educational opportunity. It's right next to some schools that students come over and they take a look at what the scientists are doing. They're able to learn a little bit more about the area, about what's under their feet that they're walking on. So it's a really cool study. So one of the ways that we measure crustal deformation is two-color EDM, which is electronic distance measuring, fancy term for laser. Basically, we have all of these reflectors set up in this manageable grid. A laser is pointed at those reflectors, and the time it takes for that laser to go from the source to the reflector and back is calculated. And as you can imagine, as those movements are happening, as those plates are sliding past each other, as they're pulling apart, that distance is going to change. Since it's happening at the millimeter scale, we can't see it with our eyes, but this laser is delicate and definite enough to pick up those really, really small differences in measurement. So I mentioned seismic gaps. These are geographical locations. So this isn't a gap in data. This is just, this is a segment of a fault where it used to produce earthquakes. Now it doesn't. So we don't see any historical evidence of it. We don't see anything happening in real time. We don't have any even small earthquakes going on. So we believe that these are capable of producing earthquakes based on what data we have, such as plate motion and strain measurements, but we don't see any earthquakes happening. So now we fast forward to 1989, where we get that 6.9 earthquake in Loma Prieta, which is right next to Parkfield. It was a pretty large earthquake, but typical of the San Andreas Fault area. They get a lot of magnitude 6s and greater, and they've developed a lot of infrastructure to handle it. Loma Prieta used to be a seismic gap. So if you look at, I know it's hard to read, but right under where it says pre-1989, the San Juan Basin, all of those red dots are earthquakes. So that has a really, really huge density of earthquakes in that area. Right next to it in Loma Prieta, there's not a lot of them at all. So this is before the big 6.7 earthquake in 1989. Now we fast forward to past 1989. Now all of them are localized in that new previous seismic gap. So all the stresses have transferred from these areas into this new area where this new fault system is now a lot more active. It's building up stresses, it's releasing stresses, and now it's a lot more capable of handling those stresses. And then we also want to get an idea of what areas are at risk, what areas are not at risk. So as you can imagine, not every area on planet Earth has the same risk of earthquakes. For example, us in Delaware, we have one of the lowest hazards of earthquakes you can imagine. We're very far away from active faults. We're very far away from plate boundaries. We have a very low risk of earthquakes happening. You get to the coast, the West Coast, where you have transformed plate boundaries where they're sliding past each other. You get a much higher risk of earthquakes. And then there are a couple of weird ones that you see out in the South. So right along this area at Southern Illinois, Northern Arkansas, West Tennessee, Missouri, that's a really ancient fault system. That's the area where we had that 1811 earthquake, the biggest earthquake known to man, that reversed the Mississippi River. So that's an ancient fault system from back when we were building the continents, back when North America was smashed against Europe and Africa, and we were building mountains. So that's a relic fault system that still has stresses in it that are slowly being released. We also have a couple in East Tennessee. That's from another relic fault system that's still slowly releasing pressures, and a couple in South Carolina from a similar thing. That's more due to subsidence, actually. But we still have a lot of surprising areas on Earth where we have those intraplate earthquakes, not all at plate boundaries. All right, so this is the modified Mercalli intensity. Is Delaware at risk to experience an earthquake? What is the answer here? Is it A? No. Is it B? How many think it's C? How about D? It's probably hard to read. Is that the problem? Yeah, that's the problem. So the one at the bottom, that's number 3. So it is actually C. Sorry about that. It's probably easier for the people at home. Yeah, so this area right here is in this dark blue. We're in the same up near Delaware. Wow, they really put Washington all the way over the state, didn't they? Well, yeah, so why isn't the answer no? Why can't we never get an earthquake in Delaware? Yeah, so we can never definitively say, no, there will never be an earthquake in Delaware, because that's prediction, right? That's us looking into a crystal ball and saying, no, Delaware is never going to experience an earthquake. It could. We had an earthquake in Mineral, Virginia. It's not crazy to think that we won't have one in Delaware. But based on the geologic setting, based on its location, sediment, and statistics, that probability is very low. So it's never 0, but it is very low. So that's something to keep in mind. All right, tell you what, 10-minute break and we'll come back. So go ahead and get some water, go to the restroom, do what you have to do. We'll meet back at 2 till 11.
Professor?